Hi everyone, in this video we're going to go through some trial exam questions. So you can see them, the questions are listed up the top. So if you need help with any of these questions, then watch this video and you can obviously fast forward where you need to. The first question we're going to start off with is question 5 from the Heffernan 2022 exam 1. So remember, with exam 1 we can't use a calculator and we can't use our notes. So it does require us to use our brain and formula sheet if we need to use a formula sheet. Alright, so the function h has a maximal domain and a rule given by hx equals log base e x plus 2 minus 1. Say the domain and range of h. Alright, so we've got a log graph. So you really need to understand what your different functions look like when they're graphed. For questions like this, you need to understand how to get the domain and range, or you might have to sketch it. So I always think about, what does a normal log graph look like? Okay, so your normal log graph comes up, crosses your axes, and keeps going. Now, this point that it crosses is when so on your x-intercept is when y is equal to 0, so that is going to be 1. Alright, so now we've got to look at our transformation. So I can see we've got this plus 2 means it's shifted to the left 2, and the minus 1 means it's gone down 1. Alright, so let's just say, well, what's happening with this point here? Alright, this point here was 1, 0. So I might just write that, 1, 0. And we've gone to the left 2. So 1, 2. So we're now going to pass through the x-axis at, oh no, we're not going to pass through the x-axis at 2 because we've been shifted down 1 as well. So, and then we've gone down 1. Alright, so your graph still also has an asymptote, so it's got this vertical asymptote at x equals 0. So that means that asymptote has also shifted across 2. So you can go 1, 2. And now your asymptote is at x equals negative 2. So if we were sketching it, it would, just trying to think where it would go through the x-axis. You can work that out, but we're just looking at the domain and range. So it's basically going to keep going like that. Now for your domain, it's your possible x values. So I'm just going to write this here. So our domain, it goes from negative 2 to infinity. Now, because you've got an asymptote there at negative 2, x equals negative 2, it's not included. And then your range, it's your possible y values. So y actually goes on from negative infinity to infinity. So there's no horizontal asymptote for this graph. So your range is any real value, or if you want to write it with infinity, from negative infinity to infinity. Okay, so just taking note of what has happened with your horizontal asymptote. It's been shifted across 2, so it's now at negative 2. Alright, part B, explain why the graph of h does not have a stationary point. So if you have a stationary point, alright, it means your derivative, alright, has to equal 0 at some point. Alright, so to have a derivative, h of x, it's when the derivative of h is equal to 0. So it does not have a stationary point because your derivative cannot equal 0. So you can just write x does not equal 0. Might be a good idea to do what the actual derivative is. So that's where you can refer to your formula sheet. Alright, so here's your formula sheet. So we're just going to scroll down. And you can see here your derivative of log, which I can't highlight, is 1 over x. So your argument, what that is inside that bracket where your x is, basically just goes on your denominator. So Let me go back to my sheet. So there we are. All right, so the derivative of hx, and what we've written there is enough because we understand that it can't equal 0. But the derivative of h is 1 over x plus 2. So that can't equal 0. So your derivative can't equal 0. So you can try as much as you like. The only way we can get that to equal 0 is if x was negative 2. But we know when your denominator is 0, it's undefined. It is not equal to 0. So I probably shouldn't have said the only way to get it to equal 0. So that will never equal 0. Your derivative does not equal 0. All right, do not say, or you could probably say that the graph continues to increase, but I think the reference to the derivative is probably the important part. So your derivative cannot equal 0. All right, so sketch the graph of the function h on the set of axes below, labeling any asymptote with its equation and axes-intercepts with their coordinates. Oh, this is where we need to actually find out that x-intercept. All right, so we did it before. I might just draw it again to show you. So our original graph came up like this. Probably should be a little bit more accurate. All right, I'm going to draw it again, just be careful. So there it goes through 1. All right, I don't think you'd be penalized for having it too out of, I shouldn't say out of whack, that's not very mathematical, but they are looking for your asymptotes, axes and axes intercepts. You do have to get the shape correct. All right, so as I said before, we do have this vertical asymptote. All right, because the graph's been shifted across 2, so here it is now at negative 2. So with your asymptotes, just make sure you draw them in pen if you're confident, or draw them in pencil if you're a bit unsure. But your graph you definitely need to draw in pencil. Now don't forget to label that asymptote as well. So it's x equals negative 2. Now our y-intercept, because this point has gone across and then down, your y-intercept is not at negative 1. All right, it does go through that point there though. So I'm going to just rub out what we've drawn. And so this is the important part of writing with or sketching with a pencil. All right, so you can use other things to help you sketch it. All right, for your x-intercept, so remember you let y equal 0, so we just need to solve for that. What was it, x plus 2 minus 1? And then for your y-intercept, we let x equal 0. So we're going to have log e 2 minus 1. I should probably do this. So 1 all right, so x plus 2. So, oops, I probably should have written this down here. Let's just go down. So x is at e minus 2, and y is at log base e 2 minus 1. All right, so e minus 2, so the Euler's number, which is e, is 2.14 something. So we're just going to be over in the positive x, so just past 0. And then your y-intercept, so log base e of 2, no idea what that is, but because we've shifted down our, and we can't actually go above, so I know that it's going to have to be below here somewhere. So when I sketch my graph, all right, it's going to look something like that. So the important things are labeling your asymptote, labeling this y-intercept. So remember your y-intercept is when x equals 0, and then there's our y. and then your x-intercept, and then the y. Sorry, the x-coordinate and your y-coordinate of your intercept. So just make sure if it says coordinates, you actually give the coordinates, not just writing the number on your axes. All right, the graph of H is transformed to become the graph of F after two transformations have been applied in the following order. So we've got a dilation by a factor of 3 from the x-axis and translation of 2 units in the positive direction of the y-axis. All right, so a graph of hx. So first of all, dilated by a factor of 3 from the x-axis. So that means we're multiplying our y, and remember, this is y equals hx. So we're multiplying this by 3. And 2 units in the positive direction of the y-axis. So we're shifting up 2. You can use mapping here as well, but your knowledge of transformations should be a lot quicker than using mapping, just because to save time. So you could, I would do it like this, and then you could go, if you had time, you can go back and do mapping, but a lot quicker just to do your 2 transformations this way. All right, so first of all, we're going to multiply the hx. So put it out the front because everything gets multiplied by the 3. So we end up with 3 log base e x plus 2. So that x plus 2 is a part of your log. It doesn't get multiplied by 3. And then 3 times negative 2 is negative 6. And then we've got to add the 2. So we're going to add, so I should probably put that plus 2 on the end. So plus 2. So 3 log e x plus 2 minus 6 plus 2 is minus 4. Sorry guys, I just realized I made a mistake and you may have picked that up. This should be a minus 1, which would then change these numbers. So let me just quickly change that. Sorry, I copied it down incorrectly. So that's going to be minus 3. So that should be minus 1. So just copied the rule incorrectly. So a good probably reminder to always just check that you're copying down things correctly. All right, so moving now on to the Heffernan 2022 exam 2 questions 1 and 3. So here we can use our calculators and we can use our notes. So I strongly encourage you to have both a scientific calculator, which is your little green one, and the CAS calculator. All right, a circular water wheel rotates in a clockwise direction at a rate of 0.1 revolutions per second. A logo showing the builder of the water wheel is attached to its outer rim at point P, as shown in the diagram below. So here. The height in meters of point P above the water can be modelled by the function ht, blah, 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 where t is time in seconds after the wheel starts rotating. So we've got 0.1 revolutions per second. And we've got this rule here. So t is time in seconds, which is important, and h is in meters. All right, so just understanding the context of the question as well. So as soon as you start seeing something round, like this was a water wheel, or if it was a Ferris wheel, you know, those sorts of things, or any type of wheel which is circular, it's going to be a trig function of some sort, or a sine or a cos function at least. All right, find the initial height in meters of point P above the water. So initial height is when t equals 0. All right, so initial height is always when t equals 0. So we're going to just do that on the calculator. You could probably do it without a calculator, but let's just do it on the calculator. All right, let's make sure we're in radians. Yes, so 14 minus 12 cos, and then t is 0, so it doesn't really matter what n is. It's really annoying when I can't get 0. There you are. All right, so it's 2. So 2 meters. Now, because it's already said meters in the questions, you do not need to repeat the units. So we can just write 2 if we wanted to. Show that n equals pi on 5. All right, so I need to go back to the question. All right, so we're going to use our understanding of these revolutions per second. So 0.1 revolutions per second. So that basically means it's gone 1/10 or 0.1 around, So this point P has gone 1/10. How many of these do we have? 1, 2, oh no, we don't. All right, so 0.1 per 1 second. So if we want to go all the way around, so what did we do to get to 1? Let's see if I can change this. We multiplied it by 10. So it's going to take 10 seconds to go a full revolution. All right, what am I doing? Go back to blue. 14 minus 12 cos. Sorry, I just need to write down the function. Cos n t. All right, so when t equals 10, your ht, I assume that's the function, can I just double check, is back to its original spot. All right, so it's back, it's gone full circle, so it's gone back to 2. And so basically you're just solving this, and I probably haven't left much space because, oh, why am I writing the wrong thing? 12 cos 10 n equals 2. Now that it is a show that question, but it's only worth 1 mark. So we can then just say, hopefully that is equal to pi on 5. Now don't just jump and write the answer. Do check that it actually works. So I'm going to just do solve on my calculator to check. So we've got 14 minus 12 cos 10, and instead of n, I'm going to use x, and that is equal to 2. Now, I'm going to show you what might happen if we don't restrict that domain. All right, so we're going to have a we're going to have a general solution, and it's also in decimals. So I'm going to go back, I'm going to change it to standard, just because I prefer an exact value. We need to see that it's pi on 5. And we get that. This we can then substitute in values of n if we like, or you can just limit your domain. So if we're limiting the domain, given that, you're going to work for me? Yep, why not give me 2? All right, so between 0 and, so what are we solving for? N. 10. Oh, we've got heaps of solutions, and they haven't put them in order. I probably made that too big. Why don't I make it? Let's change it to 1. All right, there we go. Pi on 5. All right, find the proportion of each revolution for which point P is less than 10 meters above the water. Give your answer to, corrected to the nearest whole percent. So proportion of each revolution. So proportion means we've got to basically give our answer as a fraction. All right, so proportion of each revolution for which point P is less than 10 meters. So we want T, which is the height of P, to be less than 10. All right, so let's go back to our calculator, and I've already put the function in. So can I highlight you? No, it's not going to let me. All right. So annoying. Oh, let's just write it again. I am using my stylus, that's why things sometimes take me a little bit longer. Alright, and we now, actually it's probably good that I'm writing it again because we're now going to substitute n in. What is it? Pi on 5, wasn't it? And t is a variable, so I'm going to put that in, but it's just going to be x. Now I don't like, even though the calculator should read that properly, to be confident, I'm just going to put that there. No, I've written it incorrectly. Pi on 5. Alright, is that all I had to write? NT, cool. Alright, and we've got to be less than, so time consuming, less than 10. Oh, and we're going to solve for x, so comma x. Alright, again giving us this general solution, so go back and I'm just going to restrict my domain, so we're going from 0, find the proportion for each revolution, so x has to be between, okay, x has to be between 0 and 10. Should restrict. Still giving me a Alright, I'm guessing it was giving me a general solution because we have different points where it crosses. So then I've just made it equals 10, and we've just got to know where it's crossing our graph. So what I might also do is just sketch it. Oh, good, you're going to let me highlight you. Alright, to show you what I mean. So if I just copy this and sketch it. Alright, so I'm going to paste it again. Just make sure it's out. I don't want that equals 10. Alright, and then I'm going to put in 10 here, because basically when we let it equal 10, it's basically saying I want to know the intersection between this cosine graph and the line y equals 10. So that's why we've got the 10 there. Now, very hard to see graph, so we can just go to this one to see if we can see it a little bit easier. Alright, so we can see where it intersects, so here and over here. So we need to know the proportion of each revolution for which point P is less than 10 meters. So we want it to know between 0 and this point, and from this point to 10. So I could have restricted it there as well. So that's what the 2 points on that I found here are. So it might be a bit easier if we just showed the decimal. Okay, so from 0, so below or less than 10 meters, between 0 and 8.04, and 1.959 to 10. We want to know the proportion of time. So if we go back to our graph, it's a bit easier to understand. Get it back up. And just change that so we can actually see it. Oh, that is so frustrating. I do not know why didn't put them in order. So these numbers, I don't know whether you noticed, I obviously did notice, they need to be swapped around. So let's just quickly do that. You'd think the calculator would write the lower number first, 1.959. So that's why graphing it was important, because I was like, that doesn't make sense to me. All right, so let's just quickly change that. 8.04. All right, there we go. So see how the calculator wrote 8.04 and then 1.95? I do not know why it didn't put it in order, but there we go. I'm sure there's a reason for it. All right, just going back here, I'm just going to show you how you can do it this way. So you can find the intersection this way. Might not work because I'm doing it with my stylus. All right, so you can see there's your 1.95. And if we scroll across, you can see that other point, 8.04. So basically, we want to know the difference between these two, and it's symmetrical. So basically, the whole time is 10 seconds, all right, to do one full revolution. So the time between here is going to be 2 times 1.959. All right, because it's symmetrical, it's the difference between the two. And let's just do that on our main screen. All right, 2 times, now I'm a big fan of just copying down, especially when you've got heaps of decimal places, over 10. All right, clearly we want a decimal answer, so let's just change that. So 0.39, if we need to convert it, now it did say to a nearest percent, so 0.39, or if we need a percentage, times 100. Oh, which is very annoying. All right, so 39%. Now I did say at the start, do it as a fraction, and then I realized it said to do it as a percentage, so we're converting it to a percentage, so 39%. All right, the center of the wheel is positioned 60 meters horizontally from a vertical wall. The water pipe that pours water into the water wheel is attached to the wall at point A, which is 50 meters above water. So you can see that's here. The water pipe makes a smooth and continuous join with the water wheel at point B, as shown below. Okay, I'm going to scroll. Point B lies on that part of the path of P that is given by, all right, so that is on that part of the path of P that is given by, rightio, that looks like a distance formula, where X is between 48 and 72, and X and Y are expressed in meters. Find the derivative. So we're finding the derivative of this, so dy dx. So we'll just do that on our calculator. Now just be careful whenever you're doing a derivative that your variables that you put into your calculator, if they're not the same, that you do write your answer correctly. All right, so we can just use this one here, so dx, and then type in our rule. So 14 plus the square root 144 minus x minus 60 squared. All right, just make sure that's all in correctly. No, yes. What is that bracket at the end for? Oh, okay, for our derivative. Good. It's a really annoying looking derivative. Just going to make sure I've put it in correctly. 140 x minus 60. Okay. Negative x squared. Now it doesn't say to do any rounding or have it in any certain format, so I'm just going to copy it straight from the calculator. Minus 304, 3, 4, 5, 6. Just make sure that's correct. And no, I haven't done my radical sign yet. So plus, oh, I've got a 0 here. Minus 3, 4, 5, 6. Alright, so put our radical in. Also, your vinculum, this line for your fraction, has to cover everything, and your radical has to cover everything, so don't be sloppy. Alright, and that's, well, it's only worth 1 mark, so you don't have to really show any work for that. Otherwise, you would have to probably expand that and then use the chain rule. Alright, oops, let's skip a question. Find the gradient of the water pipe in terms of B, and hence find the coordinates of B correct to 2 decimal places. Alright, whenever you see the term gradient, and this is worth 3 marks, so when I say gradient, just think there's several ways you can find the gradient. So going back to, year 9 maths, you can do your rise over run if it's a straight line. We've got our derivative. All right, and because we're finding the gradient in terms of B, find the gradient of the water pipe in terms of B. All right, so there's no B in my dy dx, so that's telling me we're probably going to have to use this. So let's just scroll up. All right, so you can see there's a straight line between A, B. So A is at the point 0, 50 and B is at BC. So let's just do that here. So A is at the point 0, 50 and B is at the point BC. All right, so just plugging it into rise over run. So just make sure I don't get the parts mixed up. C minus 50 x2 to B minus 0. So C minus 50 over B. And do we know what B or C is? I don't think so. Because it just says in terms of B, but I've got it in terms of B and C. Alright, just have to find the right one. There we go. I was looking at the solutions. So this point B, should have just read it correctly, point B lies on the path that is given by this. So our y coordinate of point B is given by this rule here. So in my gradient equation, I can just put that rule in. So we're going to have 14, they haven't given me much space, plus the square root of 144 minus x minus 60 squared minus 50 over B, and we can let that equal also dy dx. Alright, so because I've run out of space, clearly I need to do it on my calculator. Alright, scroll over a little bit. So 14 plus square root 144 minus, and if I used to find it, well, I could drag this over just to save a bit of time. 60, all right, don't forget that minus 50, just make sure it's not under your radical sign, over B. Now here I will actually use our letters just so we don't get mixed up. Over B is, oops, and we're solving, so I probably should have gone back to solve. Oh, come on. Equals, and I can just drag this down. Comma, and well, let's solve for B. Alright, so at this point I would look and be like, well, I'm not getting an answer. So what do I have to do to work with? What have I got to work with? Alright, so this x because we're looking at the point B, all right, so the point BC, so your x is actually equal to B. So when I do my dy dx, on my calculator, I just need to change my x's to b's. Let's just go and do that. Hopefully that'll make a difference. It did give me that hint in the question. Let's change that back to B. All right, so we've got our exact value. It does say to 2 decimal places, so let's just change that to, come on, there we go. B is equal to, so 2 decimal places. What was it, 64.32. And that means C, so we need to substitute it in for C. So on my calculator, all right, so our C is this part here. And I can just copy that down. There we go. Again, change it. All right, so 25.20. I'm just going to double check that I did that right. 25.20. So the coordinates of B, 64.32, 25.20. All right, so a lot of working out for, a lot of work, all right, and it is worth 3 marks. So I guess this in terms of B did help. So I knew, actually when I was solving, I was like, oh, it's just too much going on here. So changing that x to B did help, and also for your dy dx, all right, to solve for B. And then once we got B, then I could substitute that in to get C. All right, state the maximum possible distance in meters between points P and B. All right, so we're looking for the maximum distance between these 2 points. Now, what was B again? Point B lies on the part of the path. All right, so B is stationary and P moves around. So your maximum distance is actually going to be this diameter of your circle. If that makes sense. So when P is here, that's going to be the furthest distance. Now we've got to figure out how to work that out. All right, now BC, that's going to help. Let's just write that point down again. So 64.32 and 25.20. All right, so when I did that, I could straight away think, oh, I've got a right angle triangle. So I might draw that in a different color just to show you. So if I was to go down like this and across, now that's going to give me it's going to give me the diagonal, but it's not going to give me the distance between P and D. Oh, sorry, P and B. So let's just draw that over here. Actually, I'm thinking now there's a different way of doing it. I'm wondering whether I should just use the distance formula and find the maximum. All right, I also think I'm overcomplicating it because this is a cosine graph, all right, and your distance here is just your amplitude. So yeah, what's the amplitude of that? So clearly making it a lot harder than what it needed to be. What is the amplitude? All right, so it's 12. All right, so your radius is 12. Gosh, I made that so much harder. All right, so the radius, which is your amplitude, which equals 12. So the diameter is equal to 24. All right, it was only worth 1 mark, so I should have realized then I was making it to, all right, 24 meters. Find the equation of the straight line that passes through the points P and B when their distance apart is a maximum. Give the gradient and y-intercept corrected 2 decimal places. All right, let's go back to our diagram. Now, let me just thinking. We want the equation of that line. All right, so we can definitely use our understanding of this triangle to do it because the gradient is the same. So we're going to have, what was that, this distance? Oh, all right. No, my height is, so we know this is 25.20. Sorry, I'm thinking, I probably should do the question and then talk instead of thinking while I'm doing it. All right, I'm going to rub some stuff out because I did miss this. Okay, so here we've got a right angle. And we want to know the equation of this line. Now, because we've got this right angle here, that actually means those 2 lines are perpendicular. All right, so remember perpendicular lines meet at a right angle. So my triangle over here is probably unnecessary, but maybe we'll come back to that if we need to. All right, so the gradient of the line AB. Now we worked that out before, I think. Or we can just do it here. So our run is 64 point. All right, I'm just going to write these points down before I forget. Oh gosh, so we've got the point 050 and our other point is 64.32, 25.20. All right, so we're going to use y1 over, sorry, y2 minus y1 over x2 minus x1. All right, so 50 minus, and I'm just going to drag because more decimal places are always good. And then we're going to divide that by negative, and I should have that number up here. Cool, there it is. And I'm just going to change it from standard to decimal. So negative 0.3856. I think we did that before, didn't we? 3856. So if we want the perpendicular gradient, so the gradient of PB is just the negative reciprocal. So we're just going to multiply it. All right, so we multiply it by -1, so all over the place. So 0.3856, so multiplied it by -1, and then we flip it. So this was basically over 1. So now this is going to be 1 over. So I probably should have done that. And clearly we don't leave a decimal in a fraction, so we're going to go 1 over, and we can just drag this. So 2.59. All right, so that's our gradient. Put that down here. Forgotten it already. 2.59. And then the y-intercept. All right, so just doing it whatever way you do to get a linear equation. So you can either substitute it into y equals mx plus c, or use this rule here. All right, and then you can just do that on your calculator just to rearrange. So y equals 2.59x, and then let's just do the rest on our calculator. So negative 64.32. Now I actually want to have the whole number, so I'm going to drag it. Paste times this number, so minus 166.78. All right, and then we've got to bring that 25.20 over 25.20. Again, I'm not going to use the exact, I'm going to use more decimal places, sorry, that's what I meant. 25.20, where's that number? So we're just going to copy that down. Come on. 191.98. So it's going to be minus 191.98. Sorry, forgot that negative on the front. That's a problem with doing that. Let's just change it again. There we go. 141.58. Let's just change that. 141.58. All right. Oh, a lot of work there. I think you could have also used normal on your calculator. Hence or otherwise, find the time in seconds that it takes point P to first reach the water pipe from its initial position. All right, so its initial position, T equals 0, so H0 was 2. And what is its height? Since it takes point P to reach the water pipe from its initial position. So we want to know, yeah, it needs to get to point B, which has a height of 25.20. I'm just making sure that's right. Yeah. Feel like there's more working out to do from here. First reach. Alright, because it'll just be a solve on the calculator. Let's see if we've got it somewhere up. Defining on this would have been good. Alright, so this is what we're going to use. So I'm just going to copy that. So if we defined it, I wouldn't have to keep copying and pasting it. Alright. Oh yeah, I did it twice. Good. Alright, so that is equal to 25.20. No, we want our exact values. Well, as exact as we can get. Copy. More accurate, I should say. Come on. Alright, comma x. Okay. Alright, so again, it's given us a general solution, so let's just go back and restrict our domain. So we're going to go from 0, and it only has to do one revolution, so we'll just go, so t is 10 seconds. Alright, so I just had to press pause to think about the two solutions. So if we go back up to our diagram, which is going to help us immensely, and maybe we'll draw it a different colour. Change the colour. Yeah, you weren't going to work. Alright, use my highlighter. So we've got this point at B, alright, but we basically want to know when it's this height. So 25.20 actually hits it twice. All right, it's hitting it here. This is where we get our first solution. All right, but we want this second solution. So you'll notice on my calculator, I got the 4.41. That's this first point. We want this second point here. So let's just scroll down. There we go. So it's going to happen at t equals the second value, so 5.59. Oh, it's one decimal place, so 5.6. And it's in seconds. All right, I did have a look at the solutions to see how they did it, and they did it a very different way to me. I feel like my way is more straightforward, but you can have a look at their solution as well. All right, let's move on because it's going to be a very long video otherwise. Actually, I might pause there and do the next two questions in a separate video.